Okay, so now let's go and see what's going to be the part 3 of this example we're working with. We got the same, we don't have the 100-pound vertical force anymore. However, we have the same arrangement. Now it's asking me for something different. It's telling me what's the smallest force at A, which produces the same moment, the smallest force at A. That means we will have a force at A that can be directed however we want. And we are looking for which one is the smallest one possible that will create exactly the same moment we had before. Now, the moment is being applied at O, and the moment about O, it's worth 1,200 pounds inches. So we are looking for that. Now, it's asking me for the smallest force. Now, the smallest force will come when we obtain the biggest distance to be producing that force. If we recall from the two last examples, here we had a perpendicular distance in x of 24 times cosine of 60, which was 12 inches. Then when we went for the second one with the horizontal force, we got a vertical distance perpendicular to F of 20.78. As you see, the distance increased. And when the distance increased, the value of the force actually decreased. In the first one, we got 100 pounds. In the second one, for the same moment, we got 57.73 pounds. What does it tell me? Well, it tells me that the bigger the distance, the smaller the force we need to create the same effect. So for this lever, what is going to be the best, or not the best, the biggest distance possible? That one's going to be 24 inches. That means the calculation of the moment is going to look like this. Moment about O equal distance times force, and that distance is going to be all this extension of the lever. So we already know distance, we already know moment. We just solve for the force. Force equals to moment about O over distance, which is going to be the same as 1,200 pounds inches over 24 inches. That's going to give us a total force of 50 pounds. Now, that's only half of the work. We know the total force we require to get the same moment of 1,200 pounds inches in the position O. It's going to be 50 pounds. Apply it in here. However, where is it going? Could be this one, or could be this one, or could be this one, or could be this one. The direction the force is going. However, let's recall to the basic statement for moment. It will be the force that has a perpendicular distance to an application point. So the force we use must have a 90 degrees correspondence to the distance D, or in this case, to this lever. From all of the forces that I draw in here, the only one that actually has that 90 degrees correspondence is going to be this one. So we can just erase the others. Leaving us with something like that. Hence, my force of 50 pounds It's going to have this 90 degrees correspondence to the lever. If we wish to obtain what's going to be exactly the direction, well, let's recall the rectangle triangle. We got a rectangle triangle like this. Oops. We got a rectangle triangle like this. I know this is going to be 60. It's going to be 60 degrees. So, if that's the case, this one right here must be 30 degrees. If we know the force has a 90 degrees about this line right here, okay, well, if I know this is going to be 90 minus this section right here, that will give me that this angle must be 60 degrees, or this angle right here must be 30 degrees. So we can just place an auxiliary line and state that this angle is going to be 30 degrees.